All right, good afternoon, everyone. Good afternoon, Mr. Ujjwal. And I am Josh, and I'll be your special host for today. So while we're waiting for the other participants to join the session, you may grab a coffee or a quick snack. So we shall start in a while. Thank you so much. All right, good afternoon, everyone. On behalf of Apex Global and ECC International, we welcome you all to our Xposium with the title Cooling the Future Sustainable Strategies for Green Data. Join us for an insightful hour as we dive into emerging technologies and sustainable cooling solutions and uncover practical tips and strategies for optimizing cooling efficiency and reducing environmental footprint. So, in this 1 hour webinar session, Okay, we'll understand the critical role of cooling in data center operations, discover emerging technologies and sustainable cooling solutions, and get practical tips for optimizing cooling efficiency. We also encourage everyone to stay until the very end of the session as there will be case studies and other materials that will be shared by the end of the session. Now, to introduce our speaker for today's Xposium, Mr. Ujjwal Singh Rao brings a wealth of experience in engineering, procurement, and construction or EPC. Specializing in benchmarking, he serves as a counselor at CII Godrej Green Business Center and contributes significantly to ASHRAE initiatives. His expertise spans utility analysis, energy conservation measures, HVAC design, thermal comfort, MEP design, and HVAC engineering, with diverse experiences across various companies, including Levanter Air Systems. So, without further ado, I will turn the floor over to our dearest speaker, Mr. Ujjwal. Thank you and enjoy learning.
Hi, thank you, George, for such a wonderful introduction. Uh, Let me just share my screen and let's begin with today's discussion. Just taking a confirmation that my screen is visible.
Yes.
All right. Okay. So, guys, today we'll be starting, and first we'll understand what kind of heat loads are there in data centers. And before that, we will introduce why actually the cooling is very important for data center. Going forward, we will understand what are the different factors that affect the heat generation, what are the factors that affect what kind of cooling infrastructure that you have in place. Then we'll be studying the cooling techs that are currently getting placed in market for data centers. We'll go from the cold aisle, hot aisle containment to even liquid cooling. We'll understand a bit about the free cooling concept and how you can evaluate the free cooling for your data center. Uh, then we'll discuss something about the operational best practices in cooling. And I have some case studies also with me that I'll be sharing post this webinar, and that is a takeaway home for you guys. You can take forward. So, as I said before, understanding on the sustainable cooling and to understand how the cooling infrastructure is maintained and operated. First of all, it is very important for us to understand that why cooling is so critical for data centers. So, I believe most of you are either working in data centers or have prior knowledge of how data center operates. Still, for those of you who are joining it for the infograph or information only for data centers, the server is something you can relate to something that you have right now with you, your laptop or your desktop. So there is a CPU, there's a motherboard, there's a RAM. Just like your computer, the servers also have similar configuration, similar components. And all of these components have various things like resistance and conductance, which actually generates a lot of heat while the processes are going on. And to maintain the temperature around the server such that they will able to dissipate this generating heat, cooling is placed in data center. Now that's just overview of what is the causes for downtime in data centers. And while going for various reports published over internet, I found that cooling is fourth most responsible failure which causes downtime in data centers. To be very typical, it contributes around 13% in total. Now, what will happen when the cooling goes off? So, your servers are designed to operate in certain ambient conditions. And if that ambient conditions are not met, or the temperature is going above certain limits, then initially your processes will not be able to process and will start slowing down. Your performance will slow down. If you are using the website that is hosted in some of the data center, that website will take longer time to load, which will start lagging. And eventually, when the heat dissipation is completely failed, the server, to avoid any thermal damage to the components, will initiate a self shutdown sequence, and ultimately our whole data center will be down. And all the users using all the applications that are running from the data centers, they'll not be able to do so. If you talk about specifically the failures of the cooling side, then chiller malfunction covers the highest probabilities in out of the total 100%. You can say in 30% of the scenarios where the downtime was caused by cooling infrastructure failure, the real responsible person was chiller. It could be any fault in the chiller that is causing that failure, followed up by pump failure, then leakages and air blockages. There are also other multiple reasons by which the failure can occur that we will learn in detail when we'll be studying our the holistic session that we are going to organize on second, sorry, 1st and 2nd July. Now, why we are studying the criticality of the cooling infrastructure right now here is, see, these figures can vary from any number, but in a general sense, in US alone, 26.5 billion is lost annually due to just these outages. And it is not only the financial loss that we are here taking care of. People have lost lives in fire incidences, and there's lot of pollution caused, lot of embodied carbon that generates while retrofitting the damaged data centers. And above and all, the company lost its trustworthiness in the market. For example, a financial institutes, if their data center goes down and you are not able to do a transition, you would likely to switch to some other banks in future for your personal transitions. And so now let's jump to the core of the topics. First, we will understand what kind of data center environment it's needed for cooling systems to maintain. For this, we are right now referring to ASHRAE guidelines. ASHRAE is American Society for Heating, Ventilation, and Air Conditioning, and they have suggested four classes A1 to A4, where the limits of allowable dry bulb temperature and humidity goes on increasing. So if you have an A1 server, you require more stringent controls on your cooling systems. Typically, the allowable range is 15 to 32 degrees Celsius, and allowable humidity is 8 to 80%, but with a maximum dew point of 17 degrees Celsius. Why the maximum dew point of 17 degrees Celsius has been put here is to avoid the possible condensation on any of the surfaces, which can cause short circuit. And like this, we have an increasing bandwidth towards when we go from A1 to A4. Typically, I'll tell you why what happens when the humidity goes too low or too high in data centers. If the humidity goes too low, then there's a chances of generating an electrostatic discharge. Electrostatic discharge is something that when you stand on some woolen cloth or something and you rub your feet and then you touch something, there's a small spark between your fingers and that surface. That is electrostatic discharge that is generated because of the potential difference generated between you and that surface. Similar thing can happen to data centers, and uh, large electrostatic discharge can short circuit the components and can even cause fires. Let's begin first understanding what kind of heat loads are there in data center. Why the data center is generating so much amount of heat that is need to be dissipated. So the prime reason for the heat generation is your central processing unit. This is the thing that is placed inside the servers, and there are two kind of losses that actually generates heat from a CPU. Number one is your processing losses that comes with the billions of the calculations that CPU is doing at any given point of time. It can be your application to book your cabs, it can be your food delivery apps, or it can be very complex, something like a rocket launch. Everything the CPU is doing, it will be some electrical resistance is involved in doing those processes, and that electrical resistance will generate some amount of heat. Now, on the other hand, even if the CPU is less active or inactive in nature and it is not performing any processes right now, there are zero users for that application. Even in that circumstances, some kind of heat will be generated from your control circuitry and fast memory cache. And that actually is not very much, but it is very important because in data centers, there are a large number of idle servers at any given point of time. So picking up servers that are having very high efficient during idle time is very important. Just like CPU, RAM, which is also there in your local desktop and laptop that you are using right now to access this webinar, also generates heats for storing and reading and writing of the data. Similar to RAM, the large HDDs or STDs, basically when you watch Netflix or Amazon Prime or any of the OTT platforms, the data has been stored in these STDs at some of the data centers, and it's getting retrieved from there while you play. So it's multiple writing and taking away going on these STDs and STDs. STDs are solid state drives and are typically more efficient than our traditional hard disk drives or HDDs in storing data, and they have a faster data processing speeds as well. Last but not the least, and for the data center facility management guys, the most familiar thing that you know from the heat generation point of view is server fans. As we all know, server fans contributes to around 5 to 10% of the total heat generated by the service. And that is why it became very fascinating when we learned that in liquid cooling, the server fans will not be required at all. So by default, just because of this, even the PU is a secondary matter. The overall IT load requirement has been reduced by 5 to 10% because of this. Last but not the least, we have power supply units. Power supply units are basically the units that convert your AC power to DC power on the server component level. And they are typically always on, and they have some fixed consumption as well, which generates some amount of heat. So in the graph that is there in beneath, you can clearly see that the most major component that is generating our heat is central processing unit. Typically is around 60%, followed up by RAM. And the least is fan, but I won't say it's the least. Actually, this is the one part where we can eliminate by converting to a better cooling technology. Remaining everything else is probably going to be there for a longer time. Now let's talk about the things that are not there in server but still contribute to the heat loads of the white space. Typically, lighting is one of the features, but with the use of LED lighting nowadays in all the data centers, the load from lighting has been reduced to a very minimal level. For more guiding on what should be your lighting power densities in data center, you can refer to the standard SU 90.1. Apart from this, there are isolation transformers. Isolation transformers are basically used to create a neutral point for electrical safety of your data center, as well as it also reduces the harmonics that can be passed upon to your UPS. And because of this, nowadays, though we are trying to eliminate isolation transformer from the whole circuitry, for majority of data center, still isolation transformer is part of their electrical power tree. So these isolation transformers are mostly placed in your rack power distribution units, and due to their core and winding loss, just like a normal transformer, they generate some kind of heat. Now there's a new addition which normally we don't account for when we talk about heat loads, and that is your precision air handling units or PAHUs. So whatever the power you are giving to your PAHUs, that is going to get converted into heat due to the inefficiency of fan. So even if your fan is consuming 3 kilowatt and you have 10 PAHUs in a row, then 30 kilowatt of heat is being added constantly to your data center from the devices which is supposed to cool the air. So having a very high efficiency fan, typically a EC fan is very much required to minimize the heat generation from the power. People generally doesn't contribute a significant amount of heat to data center, but for just our knowledge, one person is typically equivalent to between 60 to 100 watts, depending on its metabolic rate at that point of time. And since there's not much occupancy in data center, we can eliminate it from the heat load calculation. There can be some external factors also like heat gain from sunlight, windows, poorly insulated walls, etc. This is typically not common for large hyperscalers or co-location data centers, but for some of the small enterprise data centers, these factors still play a vital role in calculating the heat loads. Now, moving from your white space to your UPS room. So in UPS room, why we require to calculate heat loads is UPS room, just like your white space, is a controlled environment, and failure of cooling in your UPS room will lead to failure of UPS eventually, and it will be failure for all the power that is going to your IT devices. So it is as important as the IT room when it comes to cooling infrastructure. Now we'll start with the transformer losses. Now many of you will be understanding that there are two kind of transformers that is being used in data centers. Earlier, we used to have normally oil cooled transformer that were placed outside the data center building in the open area, and it was naturally cooled by the airflow. But with the modularity that is coming up in data centers, now dry type transformers have started getting included, and these dry type transformers are generally keep in your LT panel or ST panel rooms, and it contributes minimal, but it still contributes to your heat load in data centers. So for non-electrical side of people, transformers generally have two kind of losses. One is core loss and one is copper losses. Core losses is defined by the amount of hysteresis and eddy currents that is generating in the magnetic core. And copper losses, as you are aware, is due to the resistance that is forming up in the secondary coil because of the voltage conversion. Now, apart from transformer, we talk about the UPS. So I'll be running very fast on these because I think most of you are already aware of these things. But just for the sake of information, the power electronic losses. So you know your UPS is comprising of a rectifier inverter circuit, and it has capacitors and some inherent inefficiencies also. All these things contributes to the heat that is get dissipating from your UPS. Typically nowadays, with modular UPS, hot swappable UPSs that are there in market, we can expect around less than 3% losses from the UPSs itself. In some cases, it is even gone beyond 2%. The best we have seen right now is 1.9% loss only. So typically 91.8% efficient. But apart from UPS, you charge your batteries whenever you use your battery for discharging as well. Both process of charging a battery and discharging a battery are not 100% efficient and generate some amount of heat. Even the self discharge also happens in battery that again contributes some amount of heat loads into data center and should be taken care while calculating the size of your cooling system for UPS room. And similarly, the control circuit, just like your IT devices, the UPS also have some control circuits because of now intelligent UPSs, smart UPSs that we have. That also contributes minimal, but to your heat load. Now, I've given the headline here: heat generation in other areas. Why I've said other areas? Because normally these BMS rooms and lobbies in other areas, uh, data center design doesn't recommends using chiller for these areas, and they keep chillers secluded for DIT space and UPS room. Other areas normally they put VRF or some other kind of standalone devices for cooling, so that the overall chiller circuit remains primarily for the core areas only. Let's talk about the factors that is affecting the cooling infrastructure in first place. So I understood a bit about the climate of Philippines, and I found out there are four typical kind of climates that is prevalent. And if I talk about Manila, it pronounced have wet from November to April, and dry from November to April, and wet from for the rest of the year. So why understanding this climate is very important is a humid climate will introduce humidity inside your data center because of some of the air infiltration that is going to happen. So there will be some amount of latent load also that you need to be removed from your data center. And if your external temperatures are going way too high, then you need to have chillers of higher rating, or you need to have the chillers that are rated as per the climatic conditions or the highest temperature that goes in your specific location. And with lots of dry season, you will have lots of sunlight that will be adding to the heat gain for data centers and should also be taking in accounted for. So all these factors helps and decides you what kind of cooling infrastructure you require, which will be best suited for your data center. Apart from location, what kind of equipment? So as you know, the racks can go from a minimal of 5 to 6 kilowatts to even nowadays it can go up to 80 or 100 kilowatts also. So depending on what kind of processing you are having in your data center, what kind of IT devices you have, will be defining the type of cooling system that you will be placing in. We'll be talking in detail on selection of these cooling systems based on IT devices in later slides. Then again, what kind of airflow management you are having also will be placing a good amount of role. And there would be some other factors like uh, your power system age, that how reliability is there on other infrastructures. That will also be putting a question of what kind of redundancy you require in cooling, what kind of architecture in terms of chill water piping, or what kind of walls you require, what kind of level of monitoring you require. So all these factors contributes to what kind of cooling infrastructure you actually need to place. Let's do a small exercise and let's see if we can do some calculations, or we can understand how these heat loads have been calculated for data centers. In the previous section, where we learned about what kind of loads are there, how they are getting generated, and everything, is actually not much relevant when you are be calculating heat loads, because in actual data centers, you just need to find out what is the power consumed by a certain device to know what kind of heat is getting generated out of this. So, as you know, heat, the electricity or the energy cannot be created nor be destroyed. So, whatever energy is going inside a device and whatever energy is coming out of that device, the difference between the two is your heat generation, as simple as that. So, if we talk about the IT equipment, there's nothing from the power perspective that's coming out of it. So, typically, you can say whatever be the kilowatt consumption of your IT device is directly getting converted into heat. Now, if we talk about UPS, as we said, typically the range of efficiency is 90 to 97%. For actual or correct estimation, you need to measure the input of your UPS and output of your UPS. The difference between input and output is your heat generation, and it covers everything that is connected to UPS, like auxiliary things and as well. Similar thing goes for power distribution unit. You can simply calculate the input outputs, and you'll be able to find out how much the heat generation is there from those devices. Now, if you are in designing phase of your data center and you don't have this data on hand, you can refer to the manufacturer catalogs and you can check the estimated loading on each of your component, how much it will be. Then there will be a manufacturer curve who will be showing efficiency versus loading pattern. use that graph and find out what will be the efficiency of my equipment at a certain load. And by that, you will be able to analyze what would be the heat generation from that specific equipment. This also we're going to learn today in our session in a bit more in coming slides. This is the conversion table that I think most of you already know. So when you procure chillers, the normally we talk in tons. So I have converted those tons to watts. So to convert 1 ton, you need to multiply by 3530 to convert into watts. And when you select your IT devices, normally from the European countries or they normally denote it in BTU, British thermal units, BTU per hour. So to convert it into watts, you just need to multiply by 0.293, and that's how you can take everything into a single units, and it will help you doing the calculation easily. Similar thing goes with the lighting, because there's nothing electrical coming out of the lighting. Whatever the power consumed by the lighting is going to convert into electricity. People, as I said, you can take the average of 100 watts per people, because the overall contribution is not much. Excuse me. Then for external heat, you need to either run a small simulation uh, with the building architecture in place in some of the simulation tool, or you can use normal Excel sheet having the U values of the wall, U values of the glass, and the amount of sun radiation that is falling, and you can roughly calculate what would be the amount of external heat load. Though in compared to the heat load generated inside, it is not much in value. So let's try some random examples. So IT equipment, since we already have discussed, there's no need to do calculation. You can simply choose the power consumption as heat load. UPS system, as you can simply put forward the power rating divided by the efficiency. So if currently your UPS will be at max will be consuming 10,000 watts and your efficiency is 95%, then you can get a heat loss of 529 watts of total heat loss. Just give me a second. Yeah. Sorry for the disturbance. So just like this, we have power distribution units, and you can simply convert the input outputs, and you will be able to find out the heat losses in a similar manner. Uh, on the right hand side, the image that you can see is the thermal image of how the air is passing through cold air and hot air line. We'll be discussing in detail this image when we'll be talking about the cooling technologies that is coming up. So this is some basic calculations that you can use and do the calculations. All of this we already have discussed and explained. So I'll not take much time on this one. This is the actual heat load calculation, or the actual, you can say, design pre-calculation document from one of the large data centers. Typically, it is from India, but the same company operates in Philippines as well. So I thought it will be slightly relevant to you. So right now, as you can see, most of the data centers doesn't build the overall data center on day one. They rely on when the client will be coming up to occupy the space, and along that they module their data centers in phase-wise manner. Here they have distributed in 6 phases, where each phase is having an IT capacity of 3 megawatt each. Now, for that purposes, they have calculated the losses that we are going to incur in PDU, electrical room, from building envelope, piping in, heat loads. There's no loss they have mentioned again the thermal storage unit because you don't have one. But ideally, if you have a thermal storage unit, there will be some self discharge loss also. Then total fan heat gain is the heat gain from your power systems, the fan. And why calculating all those factors that is there in place, they were able to come up phase wise how much heat load would be there in my data center. Now, why they have calculated it phase wise here is they'll be able to select their infrastructure in a cost effective manner. So if they know by year two, we'll be only having phase one and two in place, or maximum to maximum, we go up to phase two from the client side, they will order or procure chillers that is required for only phase one and two on that front. They don't procure everything on day one. So these calculations that we are trying to understand right now is not from only the engineering perspective, it is very important. This is also very important from the financial perspective because the overall financials of a company is limited, the budget is limited, and being engineers, it's our duty to take maximum use or optimize that financial budget to give maximum reliability to the company in terms of your cooling and electrical infrastructure. And this sheet helps you to take an informed decision in that manner. So this is just the pie graph of what we studied in the Excel sheet in the last slide. So as you can see that though IT load is contributing to almost 83.2% of the total heat losses from the white space area, the second highest comes from your Pahu fans, which normally we don't acknowledge to that extent. So this is I wanted to have you as a takeaway from our today's session that uh, while going for heat loads, please ensure to have maximum efficiency possible in your Pahu fans. Now, we also discussed that we would be having cooling for other rooms. So this is also a live sheet of an actual data center. And what they have done is they have put VRV units for other areas like security control room or your BMS rooms or battery rooms 1 and 2, your fire command center, etc., etc. They didn't dwell too much into the heat loads. They just estimated some heat loads and they put one working and one standby unit in most of the cases. So this is important because you are isolating your chiller circuit from going spread out in all of the spaces in data center. It will help you to figure out if there's a failure in your piping circuit, chilled water piping circuit, or if it's a failure in somebody else, we'll be able to manage it quite easily or quite effectively if it is centralized to only critical zones and the other zones are supplied by VRF. So, with all those discussions, I think it's time for us now to check out the cooling technologies that are currently applied in the market. We'll study some of them, we'll study their pros and cons, and we'll study why they are currently there in the market. What are the benefits they are giving to the client? So today, what we'll be covering is we'll be covering raised floor cooling, both cold aisle and hot aisle containments. We'll be covering on in-row cooling technology. We'll be covering on rear door heat exchangers. We'll be covering on D2C or direct-to-chip cooling, which is also a partial liquid cooling, you can say. And last but not the least, fully liquid immersion cooling, single phase we'll be studying. Going for race containment, the cold aisle containment is the most common technology that you must have seen or encountered in your data centers. What here we are doing, or in fact, before going to all the cooling technologies, let me just give you the thumb rule. The distance between your cooling unit and your server will determine the efficiency of your overall cooling structure. This is my personal experience that I have understood by studying all those systems. So when we say cold aisle containment, I have a Pahu located at a distance place in a mechanical gallery, and it is supplying cool air to the plenum, that is false flooring. From that, the cold air is coming inside. As you can see here, these blue arrows, and there is a contained zone which with getting filled up with this cold air. And there are servers on both sides that are sucking up this air through IT fans. And these IT fans are pushing away the hot air back, and it is getting collected in false roof or false ceiling, and it is sent back to your Pahu for cooling. That is your cold air containment in a crux. Similarly, the opposite of cold air containment is hot air containment, where instead of capturing the cold air inside a containing, you are capturing the exhaust hot air inside a containing, and the overall room is filled up with cold air. Now, you would generally have a question that what is the difference between two, which one is better, and which one is most opt for a data center. So let me just break it down to you the immediate uh, pros and cons of both the technologies. See, the cold oil is very easy to implement compared to hot oil, and it is generally less expensive also. So if budget is your primary concern, then I would recommend you to go for cold oil containment. Also, if you have a lot of retrofittings that is going to place in your data center, and on day one your full hall will not be loaded with equipments, and it will take some time for you to you. It's very easy in cold aisle just to add one more row after the other. So when you talk about modularity, then cold aisle containments is better option. Now, what sense the hotel containment is more preferable? So if you ask me personally, if budget is not a challenge, my personal favorite is hot oil containment. And the major reason or the major pros of having a hot oil containment is your whole data center is filled up with chilled air of 21, 22, 23, whatever the supply air you are having in your data center. So your whole data center is filled up with that air. So even if your cooling system goes down or something happens to your cooling system for a fraction of seconds or let's say a minute or so, you have a good amount of thermal mass of this cold air enveloping all your server areas. So it will you have a very good cushion when we say and you feel much more secure in an event of a cooling failure when you are having a hot air containment. Now, and they are considered to be more efficient in nature because since you are having abundant cold air inside, you don't need to very strictly maintain the supply air temperature to if you are having 22 to 22. A minor fluctuation is can be easily taken care by server because the air abundance is more. There can the cycling, the short cycling, and the other problems that you feel in your cold air containment, those things are less frequently observed in hot air containment. So, as I said, both of the options have their pros and cons. To summarize for you, the general decision making sentences, if you are having a very large hall, then it's suggested to go for cold air containment. If you have a very small halls or if you have a partitioned hall with airtight partition halls, in those scenarios, hotel containment may suit you better. Now, just like your cold air containment technology, where we were having the cooling system in a mechanical gallery placed at some distance from the server, we bring that cooling system adjacent to your server rack. So there are like two server racks, then one cooling unit, then two server racks, and one cooling unit. Now, how this going to help you is the air that is getting generated, the hot air that is getting generated from your containment zone will be sucked in by your cooling system then and there. You don't need a false ceiling, you don't need a false flooring for, and you don't need a large amount of pressure differences to pump your air to your mechanical gallery, and from that you need a pressurized plenum for making air their way back to your servers. So the fan efficiency improves a lot. The fan power consumption improves a lot. And since it is adjacent to your server area, the response time for any deviation in air temperature is very less compared to a normal uh, cold aisle or hot aisle system. So, but the problem is your cooling systems are taking place in your server area, so it uh, affects your economics of your data center. Each square foot of data center is costly. It's gold, if you ask me, and you are wasting some of that square feet in placing this units inside your white space. So if you are okay with that, then it's a very good technology and a very reliable, a very efficient technology compared to the traditional aisle containment systems. So as I said, the advantages are energy efficiency. Scalability is also another advantage. As you will get more servers, you can simply place one more unit as adjacent to them, and you'll be able to manage it very easily. And the rack densities for the cold aisle, I would say I won't recommend beyond 15 or 20 kilowatts. That is also on a higher side for cold and hot alignment systems. If you are going beyond 15 kilowatt per rack capacity, then I would suggest you need to switch over to in-row cooling or other cooling infrastructure technologies. The disadvantage is also there. Like it's a very high capital invest intensive process compared to our traditional cooling. A good amount of maintenance is required, and also the important factor here to note upon is that you need your people to go inside your white space for maintaining those devices. And in case of your hot and cold aisle systems, they can do it from the mechanical gallery. So sometimes in hyperscalers and co-location systems, you don't want your maintenance guys to enter inside your white space area. And similarly, noise levels can also slightly be higher compared to your eye containment systems. So you remember what I told you before. As close you will be getting to your server, your cooling systems, your efficiency is going to improve. And this is what we have done now. Instead of placing your cooling system adjacent to your server, we just place it on the backside of your server. And the technology is called as rear door heat exchanger systems, where what we have done here is these images you are seeing is actually taken from one of the data centers that we visited in Bangalore, India. So without rear door heat exchanger, as you can see, the hot air is coming out and it needs to be collected and cooled down. But if you place a rear door heat exchanger, the air is getting cooled then and there and is ready to be absorbed by the front side of the rack from that point onwards. So how we do this? So instead of placing your chiller circuit or your cooling tower circuit to your Baho system or your in-row cooling system, we place a door behind the server, and that door is comprises of lot of coils and lot of fans, small fans, basically EC fans, and those EC fans circulate over the hot air from the coils, and these coils being because it has been supplied from the chilled water, it cools the air then and there. So the air gets heats up in the server, and meanwhile it is getting exiting out, it's again become cool. So you don't require any plenum, you don't require any containment in this process. This is by far one of the most efficient process of cooling for data centers, uh, only lagging behind the liquid cooling systems. Here I can show you the circuitry, how it's been done. Let me take a pan here. So this is your coolant distribution unit, where your cooling liquid which is getting supplied to your servers is getting cooled from either your chilled water loop or your evaporative cooler or your dry cooler. Now this liquid which is getting cooled, it is getting circulated and in the coil, and this coil is placed on the rear side of your servers. So server hot air is passing over these coils and getting cooled down. And this air, the point where I'm not pointing right now, this air is now again ready to be absorbed by your server, and it will help to cool the server again. So the process, the infrastructure requirement has been reduced by a lot. The only thing is you need some expert manpower to handle, who knows the dynamics of how the rear door heat exchanger has to be operated. It can support even higher densities when we compare to your indoor cooling systems. And it is very easy to adapt this technology, and can retrofit also is possible. It can also work in conjunction with your existing indoor cooling or your cold air containment, though it will be a very capital intensive process. Then comes the direct to chip cooling or D2C cooling, what we say. So, do you remember, guys, that the total amount of heat generation, the more than 60% was from the RAM and CPU, GPUs alone. So, what we have done here is, since the, the air side of the cooling has their limitation, they cannot go beyond certain kilowatt from the rack density. And with the introduction of AI and machine learning into our daily lives, the amount of processing is getting increased on these microchips day by day, and their kilowatt is getting increased. So, what we came up with a median solution is that we will cool the CPU GPU part from a dielectric liquid, which is dielectric means they cannot conduct electricity, so there will be no short circuit while that liquid will go inside your server. So using a dielectric liquid, they will be cooling this, and then the remaining part they can cool by air. As we are running slightly short on time, we will not go into detail, but in our workshop that will be going to happen, we will in detail learn about all the components of each and every cooling technology and how they are implemented, what calculations are required, and also operational best practices for each and every of them. Last but not the least, and by far the most efficient way of cooling servers, is your liquid immersion cooling, where you literally dip your whole servers inside a dielectric single phase or a two phase immersion liquid. That liquid, since as I said, it's dielectric in nature and doesn't conduct any electricity, uh, it is safe for servers to dip those into themselves. The servers will be working as good as they were working in the air side. The only good point here is these liquids have a very high specific heat capacity compared to air, and can easily take away much more heat compared to air. And since the liquid is all around the server area, you don't require a fan to circulate the air. So your typically 5 to 10% losses that we learned in the initial phases of heat load of IT devices, that is also getting reduced. And since actually, okay, one more important thing I would like to highlight here to you guys. The CPU component is the major thing that is need to be cooled, as you already aware. The temperature typically ranges from 60 to 70 degrees Celsius. So if you are able to keep your CPU temperatures below 60 or 55 degrees Celsius, you can safely operate your data center. So in that scenario, I would say that with liquid cooling technology, even with 35 degrees Celsius supply water temperature, you will be able to operate your data centers. So typically, there's no requirement of chiller, just some dry coolers, or in some scenarios cooling towers are required. So lot of cost is saved, lot of environmental benefits are there, and from the PUE point of view, you can achieve a PUE of 1.03 is the least I've seen in the world everywhere. Physically, I've seen 1.05 myself in one of the data centers in India. This is the typical rack densities. So we were earlier used to operate around 5 to 10 kilowatts. That in early 2010s we went up to 15. Then today we are on an average operates between 20 to 40, and some of the AI processes, like, for example, if you are driving a Tesla car, the Tesla car needs lot more decisions to be made in a fraction of seconds, identifying the traffic, identifying the people walking nearby, identifying stray dogs, identifying people braking immediately in front of you, etc., etc., where the road is curving in, etc. So they require very high processing loads. So they'll be using some 80 kilowatt or 100 kilowatt density systems for their individual processing of the Tesla cars. And as I said, the rack capacities increases as we go from mild containment to immersion. As you can typically see, whatever we have discussed till now, the rear door heat exchanger goes up to 25, and maximum from immersion you can even achieve up to more than 100 kilowatts. From the PUE perspective, from the aisle containment, though it is not hard and fast rule, with aisle containment I have seen 1.3 also getting achieved. So typically it depends on a lot of other things, but to generalize, from aisle containment to liquid immersion cooling, you can reduce yourself from 1.5 to even 1.03, as I said, to be the lowest. There will be some airflow managing techniques that we were about to discuss, but since we are running short of time, we will conclude with the free cooling technologies. So there's a small exercise for you. You take the data of your city, your dry bulb and wet bulb temperature, and do this calculation yourself to see if free cooling is possible in your city from where you are attending the webinar. So what we are need to do here is let's first quickly understand what is free cooling. So in free cooling, whenever the ambient temperature of air is less than the allowable supply air temperature to your data center, you try to bring in that fresh air inside. After some filtration and measuring the air quality, you bring that air inside, make your data center cool from that air, and you then throw that air back to the environment as your sink. This is the actual image of a data center of NetApp that is placed in Bangalore, India. So from the arrows, you can see that fresh is getting intake from one of the side, and from after cooling, the hot air is getting exhausted from the other side. By using this free cooling technology, the data center was able to take away the POE to even very low values. This case study is one of the case studies we'll be able to circulate to the participants today. Uh, so in the free cooling, they have defined various modes of when the 100% free cooling will be operated. So in specific to this case, the 100% free cooling will be operated when your ambient temperatures are lower than 23.9 degrees Celsius and your RH is less than 80%. So just like this, they have calculated the thresholds, and then they found out the environmental condition that is going to prevail over Bangalore for the yearly, and they calculated their free cooling hours, which we are also going to do now. This is the weather file for Manila, and I can clearly see the weather revolves between 74 degrees Celsius to somewhere 93 degrees Celsius. Now, what you need to do is you need to find out what is the allowable supply air temperature to your data center. And what you need to do is from the weather file, the you need to find the dry bulb temperature and R in the year for which those temperature will be prevailing. For example, the 31 degrees Celsius will be prevailing for 603 hours in the year. And similarly, I have plotted the whole trajectory from 13 to 45. Now, my allowable temperature of data center is 22 degrees Celsius, for example. Then, any time where the ambient temperature is less than 22, I can use the air inside, and that is giving me 449 of free cooling hours every year. This exercise we'll be doing for two cities in Philippines during our workshop, and we'll be taking care of what will be the investment or what will be the feasibility analysis of the cooling systems during our workshop as well. There are other methods of free cooling where you can use the indirect method of free cooling the refrigerant instead of the air, and that refrigerant will be bypassing your compressor and will be using a refrigerant pump instead, as you can see in the right hand side of the drawing. And this is one of the methods very common in data centers these days, and has been now coming as an inbuilt feature for most of the chillers, and it's known as economizer mode. More details on this we will be studying from in the workshop sessions that is going to be there. Now, because the time was less, we are cutting short, and I would like to open the forum for question and answers. I would request Josh to help me up with the interaction part. Over to you,
Yes.
Josh.
Okay, thank you so much, Sir Ujjwal, for that very insightful discussion. So I think we can open our question and answer session. Let's exchange our thoughts. Okay, so feel free to ask any questions that you have for our dearest subject matter expert today, and he'll be more than happy to entertain those questions that you guys have. So anyone from our participants or from our attendees, feel free to ask your questions, please. Thank you. Okay, so I actually have a couple of questions here on the chat box. Okay, so may we request PDF copy of this presentation? Definitely, Sir Bernard. So we will be sending you this PDF presentation after this session as well. Okay. Is there new recommendation from Ashray regarding
Um,
Delta? Yes, Miss Neha.
Sorry about the confusion, Josh. So we'll be sharing the case studies towards the end of this presentation, but the PDF may not be shareable. But no worries, we will have some other exciting thoughts that we'd like to share towards the end of the session. So please stay tuned.
Yes. Okay. All right. So we will be sharing a couple of case studies with you. Like I said, like we said in the introduction part, these case studies will help you to get to know more about this particular topic that we've discussed for today. For the question of Sir Roy, I think Ms. Sherlyn have already addressed the question for this query. Now, Mr. Jaso Patrick has a question. Philippines is a humid country. If we use the free cooling, how can we control the humidity inside the server farm? So, Sir Ujjwal, do you have any thoughts regarding that?
So, first of all, Patrick, that's a very valid question that you have asked. Even when I was studying the Philippines overall climatic conditions, that was the first thing that came into my mind. So yes, when we talk about the direct free cooling, where we'll bringing the fresh air inside, I won't recommend that for most of the cities for Philippines because of the humid condition. But the indirect method where you are cooling your refrigerant from the outside air and bringing the heat exchange from the refrigerant to inside, that second amount of the second type of the free cooling is possible for Philippines, which if I had time I would have explained you in detail. You can write to us. We will give you a detailed answer on this, how we can do this, and also we'll be covering this in our workshop as well. So there you will get a detailed understanding on this.
Yes, okay. Thank you so much, Sir Ujjwal. Thank you, Sir Patrick, for that question. Any other questions before I turn it over to one of my colleagues here who has some exciting news to tell us as well? Okay, all good? Okay. Can I please see a thumbs up react if everything has been good so far? Or you can use the Zoom react button. Okay, I think most of the participants are definitely have learned a lot for this discussion. Okay, Mr. Lemuel here has a comment on the chat box as well. So I think free cooling is doable. We only need to correct the issue using basic control system. Okay, thank you so much, Sir Lemuel, for that insight. Okay, so without further ado, I will turn the time over to one of my colleagues, Ms. Sherlyn, who has some exciting news to tell us. So, Ms. Sherlyn? Okay, I have
Okay.
a, yes.
Can you see my screen, Josh? Or
Hold on a second. I think
can you
there.
share screen? Yeah.
Okay.
Okay. So hold on. So hi everyone. Of course, thank you, Mr. Ujjwal, for the wonderful presentation. And again, I am Shirley Igonia of ECCI. To all the participants, thank you for staying throughout this webinar. We hope you found this session very productive. A one-hour webinar never does justice in terms of addressing all the questions or covering all key aspects of a topic as critical as energy efficient data center. So next slide, please, Josh. So based on the great interest, we are organizing a two-day and a half-day hybrid training setup where the first two full days are classroom or on-site training, and the remaining half day will be virtual. The topics are ranging from overview to practical implementation strategies, where all the attendees will gain valuable insights to enhance the efficiency and sustainability of their data centers. Next slide, please. So, and of course, to those who attended and stayed until this end of this webinar, will receive these benefits. So first is up to
Ah,
12% discount.
3 to 4 weeks ito, 4 weeks talaga to eh.
Okay. When you register for the training, you can use the following discount code during the registration. Plus, we are also open to doing a walkthrough energy audit for any one of your data center sites during the same week of the training. The audit will last for the half day and after the 10 days. We will be able to provide you the insights on energy efficiency opportunities plus the high level saving potential for your further consideration. The audit offering will be on the first come, first serve basis owing to the limited time we can spend. Feel free to reach out to me if you are interested through the email address that posted on your screen now. And I'm happy to explain further when we speak. Thank you so much and have a good day to all.
All right. Thank you so much, Miss Sherlyn, for that very insightful announcement and discussion. Definitely a great offer for all our attendees right here. If you will enroll for the Energy Efficiency Practitioner course that we have presented to you right now, you will be getting up to 12% discount on the training enrollment fee. And not just that, you will also get a free energy audit at one of your data centers. So what are you waiting for? Reach out to us via the email that is shown on the screen, sherlyn@eccinternational.com. So I'll also be sending this email to the Zoom chat box so that you guys can send your queries there. Okay. All right, so with that in mind, I hope you all enjoyed the discussion this afternoon. I would like to thank everyone for your participation for today's event. So to properly end the session, I am sending you this quick survey that we have for you. Okay, so hold on, please. All right, so I have sent you the quick survey that we have. And we request everyone to kindly fill this out as this will generate important information that we could use for our next exposiums and any topic of interest that you would like to tackle. Once again, thank you for attending our exposium for today with ECCI and Apex Global Learning. Thank you so much, Sir Ujjwal, for your time today. Have a wonderful day, everyone.
Thank you, guys.
Thank you
Thank
so
you.
much.
Thank you so much, everyone. Have a great day.